My name is Shannon Lynch. I'm a second-year PhD student at UC Santa Cruz, but I'm also affiliated with UC Riverside. And the project I'm going to be talking about is part of a collaborative effort looking at what's controlling the landscape spread of an introduced pest disease complex in Southern California, Fusarium, Dieback, and Polyphagous shot hole borer. So this is a pest disease complex. It involves an ambrosia beetle called Polyphagous shot hole borer. It has a symbiotic relationship with a fungus, a Fusarium species. And just to give you an indication of size, these are the beetles on a penny. The female on the right is much larger than the male, which is on the left. And the female has these special mouth parts called mycangia that it uses to carry the fungus and spread the fungus from tree to tree, and that fungus is also a pathogen. And just to make things even more complicated and confusing, there was a second introduction of this pest disease complex in San Diego County, but I'm not going to talk about it. When you see distribution maps with the blue dots, that's what that is. In Los Angeles County, we primarily have Polyphagous shot hole borer. So the way that it affects trees, this is a cross-section of a branch, and basically what the beetle does is it produces a gallery or a tunnel by penetrating through the bark and going into the wood tissue. And then in those galleries or those tunnels, it inoculates its fungus and it produces a fungal garden. And this is really important because the fungus is the sole food source for the beetle. It cannot eat anything else. And so having that fungus supports its ability to, for the developing larvae to eat, to reproduce, and spread. At the same time, it's a pathogen. So the fungus colonizes the wood tissue, and the host tends to respond by blocking, creating these products that block the water conducting tissues in the plants to prevent movement of the fungus through the tree. But it ends up being an overreaction that prevents nutrient and water uptake by the plant, and that results in dieback and tree death. The pest disease complex has a very broad host range. The beetle alone can attack over 300 tree species. A subset of those, which are listed here, these 49 tree species, are the ones that support beetle reproduction. So those are the ones where it can actually make a gallery, grow its fungus, and feed the larvae. The top 10 on this list here are more affected by the disease. So when the beetle attacks, it kills the trees, whereas on the other ones, you just see generalized dieback and not tree death. Because of the broad host range, it has an impact across many different land use types, including native plant communities, urban forests, as well as the avocado growing range in Southern California. This is a distribution map of the Los Angeles area in April 2015. The red dots represent confirmed positive locations, and these diamond shapes represent monitoring traps that were established by Dr. Escalin at UC Riverside, used for the purpose of trying to catch the beetle and detect movement of the beetle inside traps into Ventura County, where it hadn't yet established. And in June 2015, the beetle was captured in 2 locations in this trap wall, but none of the trees in the area have been monitored ever since. And so the purpose of my project under this fellowship was to conduct a rapid assessment to really understand what is the most recent occurrence of the pest disease complex in the urban-rural interface in the San Gabriel and Santa Monica Mountains, as well as the San Fernando Valley, and just to get a first initial glance at potential indicators for disease spread. So at the urban-rural interface, I went to approximately 30 locations across the San Gabriel Mountains from San Dimas to Santa Clarita. I stopped around every other mile and just recorded the location, whether what host was there and what trees were infested, and I also confirmed non-infested locations. And I did a similar thing in Topanga Canyon as well, along this horseshoe, and then along Topanga Canyon Boulevard into Malibu. In San Fernando Valley, I did a somewhat more systematic approach where I took a random selection of city blocks that were a 1/4 mile squared. And within each of those blocks, I counted every reproductive and non-reproductive host and marked the general location of each infested and non-infested tree. And I was able to collect a large volume of data because I was using a smartphone data collection platform that just transferred all of the data to an online server. So I was able to get a lot of information. These two graphs represent all of the trees that I collected data on for this survey. The graph on the left is representing on the y-axis all of the tree species that I collected data on, and the x-axis represents the number of those trees. The black bars represent the total number surveyed for each species, and the orange represents, that's superimposed on those black bars, represents how many were infested. And then the graph on the right is pretty much the same graph, but it's showing the most common reproductive hosts that I encountered that were infested, which were sycamore, liquid amber, coast live oak, and cottonwood. And by far, sycamore took up the largest proportion of trees infested. So these are the data in particular at the urban-rural interface. The graph on the left is the total, the graph in the middle are the number infested, and the graph on the right is showing the proportion of trees for each species that were infested. And the interesting takeaway here is that there are a number of good reproductive hosts in the landscape. The sycamore is by far the most abundant and the most infected, which is that bar on the top. It's that top bar there. There are also some hosts in the middle that are less common, but they're also affected. And then there are also tree species that are rare. So those are the ones at the bottom that have low numbers, but the majority of them were affected. So you have a widespread distribution of a really good susceptible host throughout the landscape. And then you have rare tree species that are present, and if the beetle encounters it, it will affect it. It doesn't mean, it's not important from an epidemiological perspective, but from a species standpoint, that's important. These are the key locations where I identified for which I detected new infestations of the pest disease complex and the hosts on which I detected it. They include Sycamore, Big Dalton, Fish Canyon, Altadena Crest Trail, O. Melvini Park, Cagle Canyon, Lopez Canyon, Topanga Canyon, and Big Tahuna Canyon. Tahuga, whatever. And then the other important thing about this survey was I detected 2 additional reproductive hosts on this survey, and those were California buckeye, which is Aesculus californica, and Quercus chrysolepis, which is canyon live oak, both of which are native to California. This is the distribution of the trees that I identified, and all of this is on our interactive map online, and I will show that website at the end of the presentation. But the orange is the confirmed, the white is the negative. So I detected 550 trees, 8 were new canyons and 1 regional park. 2 new reproductive hosts were identified. Sycamore was the most abundant and widespread. And the study is limited in that I wasn't doing a systematic assessment and looking at per unit area. I wasn't looking at like a number of trees infected per unit area, but what this does is it gives a good indication at least of where it's at and will inform future methods for future monitoring studies to get at potential impacts. And this website will be shown at the last slide as well, where you can see these updates. Okay, so in the San Fernando Valley, 19, so the confirmed positive locations are in pink, the confirmed negative locations are in white. 19 of those city blocks that I surveyed were infected, so that was roughly 40% of the locations that I visited. Again, a similar pattern in the San Fernando Valley in terms of the species, but the one takeaway here is that the liquid ambar was much more abundant in that San Fernando Valley urbanscape, but was less affected by the disease. So it strongly preferred sycamore, which is that second orange bar at the top. So it's showing a strong preference for that host. And if we look at this on a per grid basis, per block, we see some interesting results as well. So the top left graph is showing the total number of trees per grid. The top right graph is showing the total number of trees that were reproductive hosts in each grid. The bottom right graph is showing the total number of infested trees in each grid. And then the bottom left grid is showing the proportion of infested trees, so the number of infested trees of the total in each of those grids. And so typically in disease ecology, what we expect is when you have a large number of susceptible hosts, you tend to see a higher degree of disease, more disease pressure. And what's interesting about this is we don't necessarily see that pattern. So you have some blocks, like this one, that has a fair amount of susceptible hosts, but a low level of disease. And then in other grids, you have not that many numbers of trees per grid, but you have a high, some of them show a high level of disease. And so when we look at this spatially, this is looking at it from a spatial perspective, and I'm just gonna step through these images for you. You can see on the right, so this is showing the distribution of the grids that I sampled to scale. And then on the left, this is a map of those exact same grids, but the size of those grids are scaled by how much disease was there. So the larger those boxes are, the more disease, and the smaller those boxes are, the less disease. And so you can see some disease hot spots popping out on that map. And then when we look at sycamore, we see this one, so the top one is showing incidence, this one is similar, but now it's showing the size of the blocks represent how many sycamore trees are in each grid, and the color represents how much disease. So if it's hot pink, there's more disease. If it's white or light pink, there's less disease. And then one other graph here is showing on the y-axis the total infested number of trees per grid, and on the x-axis is the total number of sycamores per grid. So you have some locations, what we would expect, with a large number of sycamore trees with a lot of disease, and that's represented in that top right area on the graph. Some locations have a lot of sycamore, but very little disease, which is represented on the bottom right part of that scatter plot. Other locations where you don't have that much sycamore, but you have a lot of disease, which was not what we expected. And then other locations where you had hardly any sycamores and no disease. And so this trend of the number infested trees per grid and total numbers of sycamores per grid is almost significant, but there are these outliers that are disrupting the pattern a little bit. But what this is suggesting to us is that, well, actually, I do want to say that when I did a logistic regression and just looking at the probability of the beetle getting to a location, it was significant by the presence of sycamore. So sycamore was a descriptor in that case. So what this is suggesting is that the beetle is using these locations for movement. Once the beetle gets there, whatever is happening is pretty idiosyncratic. And the limitations to this is that this is taken during a snapshot in time. So a lot of these, could be just an artifact that the beetle hasn't gotten there yet, or that the beetle has just arrived. And the arrival of the beetle in these locations have happened at different times. So there's limitations to looking at this snapshot in time. But again, what it's suggesting is at least the presence. So yeah, the beetle is using locations with sycamore for movement. The likelihood of arrival is determined by the presence of sycamore, but not the density. And so monitoring these locations over time will give us a better understanding of impacts and once the beetle is established in these individual locations. In the meantime, infested trees can pose hazards. Like this this has well over thousands of entry holes on it, this heavily infested sycamore branch hanging over a car, not really a good thing. Or heavily infested trees in front of elementary schools, not ideal situation. So one more thing. The disease, once it is established in an individual tree, we have seen that it can progress quite quickly. So this is an infested sycamore in San Diego County. It got infested in July of 2013. This is the same tree 2 months later, and then this is the dead tree in November. So it can really move rapidly once it is established in a tree. There is this management matrix that was developed by UC Cooperative Extension in Orange County, and this matrix is up on the Escalon Lab website, so you can go and look at this further. But basically, it's a decision matrix on what to do in terms of removal of trees or pruning of trees or monitoring of trees, depending on the tree status. So whether it's a low value host, whether it's a high value, whether it's reproductive or not reproductive, whether that host then poses a high hazard level or a low hazard level. So if it's in front of an elementary school and it's a sycamore, then you might want to consider removing the tree. So what this study implies as of now is that the management of trees should be focused on these locations that are like disease hotspots and focus on areas that have trees that pose hazards to people, and then use the appropriate recommendations accordingly. I made a handout that details how to assess sycamore trees specifically, and that's out on the table outside, and that handout is also posted up on the Escalon Lab website. So I just want to thank especially the LA Center for this fellowship and giving me this wonderful opportunity. I'm really grateful. And all of the other funding sources for this research, as well as the huge team, especially the Escalon Lab and other researchers in Cooperative Extension and elsewhere that have been instrumental in getting the word out. So these are the websites. And the handout that I produced is basically a guide to identify different varieties of sycamore, understand or determine the different crown conditions they have, and also to assess the severity of disease that are on a tree so that they can be assessed in a systematic way for people. So, thank you.